you guys are coming out of your fabulous nuclear atomic assault case study where you argued both the isotope identification and the verdict for Joseph Simonson's case. The real case was the dad was guilty, but he only got, I believe, 11 years in prison and a $5,000 fine. That right there is the price of a child's future. Just so you know, 11 years in prison and a $5 fine back then. Did we ever know what the motive was of the real case?
I think I heard Joseph like favored the mom during the divorce, and the dad was salty.
One salty, yeah.
He didn't like the mom, and he wanted to get back the mom by like leaving his son.
Oh, well, either way, that dad is psychotic. So, also careful who you don't make enemies where you don't need to make enemies. Okay, that's just a little life lesson right there. So you're just coming out of that, and that was really an expose on getting you guys to apply your understanding of nuclear decay, alpha, beta, gamma. You didn't do too much nuclear change reaction writing. For your test tomorrow, you all need to know how to write alpha decay. Like you need to know how to write a completed nuclear change equation for alpha decay. What law do we apply when writing nuclear change equations, Roman? What law do we apply when writing nuclear change equations? The law of excellent. So that means whatever mass amount you start with for your unstable isotope, you end with between the two particles you create, your radiation and your hopefully more stable daughter isotope. Whatever proton count you start with for your unstable isotope, you end with between your two new particles, your emitted high energy radiation and your hopefully more stable daughter isotope. Okay. Honors, you also have a beta and gamma, all right, aspect to your test where you will write the equations for beta gamma, which is very easy as long as you know what beta and gamma is. It's a very easy win for this second to last unit. And so what we are left doing now is a very, very short topic on nuclear energy. One of the questions on your test for this unit will be you describing the nuclear energy transformations that we see in industry when we do actually utilize nuclear energy, the massive scale of nuclear energy to power things. It is a really complicated topic, actually. We are going to whittle it down to like baby level and just focus on how might you just describe the successive transformations and conversions from nuclear energy at nuclear power plants to how it fuels our homes and stuff. And by the way, nuclear energy power sources is becoming a new topic in actually green energy, because if those radioactive emissions are going to happen anyway, why not package them, right? So it ends up being an actually interesting kind of topic of what does really sustainable energy look like. But we're going to do a super, super brief overview on it today. So before we get going, I would like you guys just to take a couple minutes to research maybe some applications of where we see nuclear energy currently being applied in the real world. And then also make sure you have your notes out. So take about a minute or two to research that. So when we think about the topic of nuclear energy and energy transformations and how we utilize this massive scale amount of energy from these high energy particle radiation like emitted, we got to think about two big ideas that we talk about in the NGSS curriculum. And that is the idea that energy flow and particularly energy release. We've already kind of discussed a little bit about energy flow and energy release through the idea of exothermic and endothermic chemical reactions, exothermic and endothermic physical processes. And now we're looking at it at a much more massive scale. So the big thing that you want to be thinking about when we are going through this unit and as you kind of prepare for your test is where is the original energy source? And how is it being transformed? That's what you kind of want to think about is what was the original energy source, and then how is it being transformed? Why am I seeing this energy be released? Or am I even seeing energy released? Maybe I'm seeing it actually be taken up, right? Could be the antithesis of that. And then of course we want to be thinking as another kind of subtopic is scale. Again, you've already been thinking in this kind of way by starting with the mole and the atom, right? You have been thinking at a super micro scale of a single particle, and then you got blown up to the mole and atom, Avogadro's number, 6.022 times 10 to 23 times larger, right? So you've already kind of been doing the dance of scale. And now we're particularly applying it to the magnification of energy release in nuclear processes is kind of our take on this. We're looking at the magnification of energy release in nuclear processes. And we're trying to figure out how does something so small as a source create such a large amounts of energy? And then how do we use that? And then I guess the next thing is you can say is how to utilize. Right? That kind of is the ultimate question that we get into. So, one thing that you should know is that's really obvious is that when you think about nuclear versus chemical energy, nuclear energy is exponentially greater than chemical energy. Which makes sense. Like when you do a chemical reaction, you're like, even a combustion reaction is like, oh, that's like bad. Like you could blow up a gas station. You could blow up a house. But you're not exactly concerned that like a reaction gone wrong is going to blow apart your entire city, right? Very different scale. So nuclear is always exponentially greater than chemical in terms of energy release. Usually it's like a few thousand times fold, few 100,000 times fold. Okay. Given the same amount of particle starting reactants, if you were to do a nuclear process with like 5 grams of some unstable isotope versus a chemical process with 5 grams of another reactant, guarantee you those 5 grams of nuclear reaction would be a lot more damaging than 5 grams of a chemical reaction, right? But both still obey the law of conservation energy. It's the universal law. So both forms of energy, despite being at different scales, still undergo transformation. So both types, okay, still follow law. So they are transform or convert, but are not destroyed. And this is what we actually capitalize on. This is what we're trying to do in industry is knowing that we have this incredibly high scale, high magnitude energy source or energy releasing process. How can we actually utilize it to bring about benefits to society and our everyday life? So what we're going to do is we're going to watch a little video, and you're going to be focusing on how does these two power plants, one chemical based, one nuclear based, transform one source of energy into another. That's what you're going to be focusing on. You're going to want to pay attention to the individual parts of the power plants that kind of represent phases of transformation. It goes through about a 3 to 4 step energy conversion process. By the way, these power plants are like towns, the size of towns. They're huge, and they're often built underground. And if they are built above ground, they're built on the remains of another power plant usually. It's kind of funny. So we're going to start with the coal power plant. This is very much the chemical power plant. I just want you guys to take notes. Don't really know why this is showing up here. I want you guys to take notes on the energy transformations and where you see it in the actual building structure. Is it when it goes through the generator that you get this heat transfer to this heat transfer? Now, remember, when we talk about energy transformations, you're going to think about kinetic and potential, chemical versus thermal versus electrical versus mechanical versus nuclear. Those are kind of like your themes. It will also walk you through it in the video, and that is not the video I wanted. So give me a second. There we go. Is it not playing up loud?
So electricity is basically the movement of electrons through a material. What are the main sources of electricity
Why is it so
though?
quiet?
This light globe is being powered by this battery. But where is the
Why
electricity
isn't it
powering
playing through the
this?
TV? Does anyone know why it won't play through the TV? All right, everybody, I'll put the CCs on and it's gonna be kind of quiet.
So electricity is basically the movement of electrons through a material. What are the main sources of electricity though? This light globe is being powered by this battery. But where is the electricity powering this light globe coming from? Well, most of the world's electricity comes from coal-fired power stations, gas-fired power stations, nuclear power stations, hydroelectric power stations, wind farms, and solar panels. All of these generate electricity, and the electricity is fed into wires which carry the electric current to our homes and industries. This whole system of wires is called the grid. The things that produce electricity feed electricity into the grid. Let's take a closer look at them.
So when we think about the transformation, the ultimate goal is in industry is to take nuclear energy and yes, do all the things that you've just named earlier of applications, but turn it into how can we use nuclear energy to particularly fuel the mechanical logistics of everyday life. So instead of maybe plugging in your phone and just assuming it's electricity from, you know, the rubbing of two metals together or whatever, instead maybe your phone is actually, electricity is actually the result of a nuclear energy source being transformed into electrical source, powering something. So that's kind of where we're headed with, although it is interesting to hear how it is entering the medical field in that kind of sense. But this is kind of our focus for this unit.
This is a simple generator. When I turn these coils of wire that are surrounded by these magnets, electricity is produced. This is another much smaller generator. When I turn it, you can see from the voltmeter that it produces electricity. If I connect some LEDs to it, the LEDs light up when I spin the generator. Most of the electricity that is generated in the world to power our homes and our schools and our industries is produced by generators. Over the past 100 years or so, the huge generators in coal-fired power stations, like this one, have been the #1 source of electricity in the world. So how do they work? Firstly, the coal is dug up by huge excavators. This one's called a bucket wheel excavator. It's
little
about
nephew loves
200
that
meters
excavator.
long, but most aren't quite this big. The coal is then carried by conveyor belts into the power station, and it's fed into huge boilers many stories high, where it is set on fire. The water in the boiler boils and turns to steam. The steam is forced up through pipes into huge turbines. The turbines are kind of like windmills, and they spin as the steam pushes on them. This is what the turbines look like. They're normally enclosed, but here they are undergoing maintenance. Each turbine is connected to a generator so that as the turbine spins, the generator spins as well. As we've seen, electricity is produced when any generator is made to spin. The hot steam is then cooled down in the condenser so that it condenses, and then the water is pumped back into the boiler so that the cycle can repeat. The condenser is kept cool by cool water that is pumped into it either from a nearby river or lake or from what are called cooling towers. The white clouds that are often seen above cooling towers are made of water that has evaporated in the cooling process. Coal-fired power stations need huge amounts of coal, of course, and because it's difficult to transport coal large distances, most of them are built near coal mines so that the coal doesn't have to be transported very far. Transmission lines are constructed to carry the electric current to our towns and cities. Now, gas-fired power stations work in pretty
Okay,
much
we'll
the
pause
same
there.
way as...
So let's go back to our notes for a second. And what we see is with the coal power plant, which is our example of a chemical process or chemical energy release process. We see that we start with coal, which by the way is huge and very tedious task. It is not ideal. So just generally speaking, also when we compare the nuclear versus the coal, you're also going to see some logistical issues, right? Coal, which is a very large, right, starting material. It's heavy, it's dense. You have to do a lot of work to harvest it. Okay. What happens is the coal gets burned. Okay. If you're burning something, you are doing a chemical reaction. That is a chemical reaction. And what you are generating is when the coal gets burned, you are generating heat. And as a result, that is what we call thermal energy. So what you do is you're taking your chemical energy and you're turning it, okay, into thermal energy represented by the creation of the steam, right? Because what you do is you heat up the water, producing a steam. And from that steam, all right, what you get, and I should say heat up water producing steam. What you get is now you have a steam that is then, I believe, put through a turbine. It powers a turbine, right? So what it does is that steam powers a turbine. Okay, that's kinetic energy. That thermal energy has now been transformed into kinetic energy to push the turbine. And then what we see is when that turbine spins, that turbine runs the generator, right? Okay. Produces electricity due to the spinning. So then what you get is you get chemical energy, or sorry, electric energy. And that electric energy flows through our homes and powers our mechanical. And then it gets sent through the wires and powers our devices, which is an example of mechanical energy in action. So what you see here is a quite thorough succession of energy transformations where we take one original form and we send it through a series of stages that allow it to be transformed into a useful expression of itself. Now, obviously, there is some energy lost throughout every successive process. That's a no dirt. But what you see is an actually very brilliant energy example of Rube Goldberg machines. Have you guys heard of Rube Goldberg machines? It's the same idea. It's just with energy versus with, dominoes falling. But it's an actually incredible thing that we can take something that is actually quite toxic. Like I wouldn't say go burning coal is a great idea. And we can turn it into a source of progressing the human daily experience and meeting the needs, right, of our progressing world. Now, obviously, though, we're seeing a problem with these chemical-based power plants. They're huge and the materials are huge. So per volume of space, the amount of an original reactant that you need to store, you can't store as much as you want to. You're constantly supplying, and notice they have to be very strategic about, they have to be put a lot of money into transferring from the coal mines, which somebody has to mine those, and to your factory. And by the way, once coal's burned, it doesn't exactly regenerate itself, right? It's got a pretty short expenditure lifetime, right? And so this is where we hop into the nuclear power plant, kind of this idea of how can we start looking at nuclear energy as the future of energy source? So we're going to go to this one now. Is this gonna work on me? Okay. The movie's starting.
Nuclear power plants, like fossil fuel plants, produce electricity by generating steam that is used to
Nuclear power plants, like fossil fuel plants, produce electricity by generating
No
steam that
CC.
is used to turn a turbine and generator, which then create electricity. The primary difference between nuclear and fossil fuel plants is the fuel source that is used to produce heat, which in the case of
Pause.
nuclear generation results in no
Nuclear
greenhouse
power
gas
plants are
emissions.
considered a green movement in energy. Why? Because no greenhouse gases, which we attribute to the global warming effect, are produced. The burning of coal is in super toxic byproducts. Ironically, nuclear, despite the radiation, is pretty good. Pretty good, especially if you can contain and trap that radiation. If you can contain it in such a way that it's not exposed, that's awesome, right? But coal mining, what you do is it's really hard to contain those gas. Let's put it that way. So quick note, you might want to put that on your notability, which is automatically something to consider about the difference between Diablo power plants or the nuclear power plants is one, when you look at nuclear energy release, it is a benefit that there's no greenhouse gases. So it is considered a green form of energy. Again, very surprising considering the radiation part of it, but it is considered a more sustainable energy source. And then of course, two, well, we'll keep going. Well, I guess, and then of course the other difference is that you're starting off nuclear, but let's keep going with, where's my Safari? There you go.
At nuclear power plants, the heat to make the steam is created when uranium atoms are split in a highly controlled process called fission inside a nuclear reactor.
Okay, so we see that here our starting reactant is, or our starting process is the fission of uranium, a specific isotope of uranium, producing what we call, right, nuclear energy. Okay, radioactive energy. So already we're seeing a difference. And also, by the way, already we realize something, that energy release is so much larger than the chemical energy release. Like already we're just starting off with more at the beginning. So as the successive chain of transformation occurs, right, we have more to work with from the start. So we're going to still end with more, even as the transformations are occurring. Okay.
There is no combustion in a nuclear reactor. The uranium is in the form of fuel pellets that are placed into long rods and then into fuel assemblies, which are then placed inside the nuclear reactor, which is filled with water and is inside the containment dome. Throughout the fission process, radioactive material is designed to stay inside the fuel pellet.
So they, like these little containers, the pellets of radioactive material, are strategically structured so you can trap everything, which is brilliant. It's brilliant. And also, by the way, as we know, if you know the type of decay that is being emitted, you can build the type of device that you need to contain it. Easy.
In this animation, the nuclear reactor is in the middle attached to the 4 steam generators with pipes. The fission process inside the reactor heats the water to over 600 degrees, but because it is under pressure, it does not boil. The pumps circulate the water between the reactor and the steam generators in what is called a closed loop, and keep cycling between the 2 components. When the heated water reaches the steam generators, it goes through thousands of tubes which transfer the heat to water in a separate system
So
where
it's
it is
looking
turned to
pretty
steam.
similar now.
Water from
This
the
is very
reactor
similar
and
to
the
the
water
coal
that is
plant.
turned into steam are in separate systems and do not mix. The steam is then piped from the steam generators and the containment dome to the turbine building. Inside the
Okay, we
turbine
moved to a
building,
turbine
the steam
building,
pressure
too.
is directed to large fan-like turbine blades.
Notice
inside the
though how
turbine
much
housing.
more
The
massive
blades are
this
attached
is.
to a shaft that in turn spins from the pressure of the steam. Also attached to the shaft is the generator, which consists of a large electromagnet that turns inside a stationary coil of wire. This turning motion produces electricity. At Diablo Canyon, no priority is more pressing, no responsibility more important, and no commitment more fundamental than the safe operation of the facility. That same focus on safety extends to responding to emergencies at the plant.
Okay, so what we see then is with the Diablo power plant, we actually get a pretty similar storyline as the coal. That was a mistake. We get a pretty similar storyline as the coal, where you get the following transformations. Your nuclear energy, okay, is actually transformed into a type of thermal energy where you produce steam. Your steam powers a turbine, which is kinetic. Your generator produces electricity and then it goes to your homes. The biggest difference is you end with so much more. You use the same overall process in terms of transformations to get the product that you want, but you end with a much more massive scale. And that was kind of the big idea that NGSS wanted you to think about is, why is that the case? Why do we even study nuclear decay? Because in colleges, you normally don't study this topic. This is a very interesting take that the California state standards have taken to actually include this. And it's because the future of energy is heading toward nuclear. And in addition, the idea that when you study processes, the eventual goal is to utilize it somehow. And nuclear is fascinating because it's this really obscure thing that we only know about through history as this terrible, awful, inhumane, unethical tool. But it's being transformed into actually a staple of continuing to provide the needs for our 8 billion plus people. So, and it also, of course, just incorporates the big ideas of energy, scale, transformation, stuff like that, that is big subtopics in the curriculum or common themes that you see across. All right. So big idea. What would you guys say is the big idea? Go ahead and write down your summary statement of the big idea about nuclear energy transformations and nuclear processes. So I would say the big idea from this is, one, nuclear processes or nuclear reactions produce way larger scale of energy. Like that's the main idea, is that nuclear processes produce way larger scale of energy. And then two, okay, nuclear energy can be transformed. Right? So that's a great thing to know, is that nuclear energy is not outside the laws of the law of conservation of energy. For your test, you will be asked to describe basically what I wrote up here, the energy transformations through a nuclear power plant. How do we get from nuclear to mechanical? You will be asked to describe that 3 to 4 step process and tell me, identify what parts of the power plant you see that transformation occurring. Okay. For the test, you will be asked to explain and write the nuclear change equation for an alpha decay, and then explain it verbally. When I had you write in your description, okay, sorry, I'm just going to scroll up for a second. When I had you write in your description here, describe the process, you will be asked to do a similar thing where you not only take the equation model, but you also tell me it, verbiage, full sentence. All right. And then honors, you will be asked to do it with beta and gamma as well. It's not that hard of a test. It's actually really short. It's just making sure that when you answer the test questions, you answer it fully and you answer it well. Okay. You all have access to a practice test. I printed one last week, so you should have it. Okay. The rest of class is time for you spent studying on this test. And of course, getting in any old work because all unit 6 work is due tomorrow. All right, guys. So, and if any of you guys are in seminar, you have to go to your registered seminar and then get you the golden ticket to come back to me. All right. Good luck on studying.